Okay, so in this video, we're going to prove proof by induction. So what I mean by this is we're going to show why proof by induction is indeed a valid form of proof. So we're going to state it as a theorem and attempt to prove it. And this is the theorem. We have that for each n in n, we let P of n be some statement for n. And we want to show in the end that P of n is true for every n in the natural numbers. And we're going to make two assumptions. Assumption A is that P of 1 is true, so that the statement holds for n equals 1. And assumption B is that for every n greater than 1, every integer n greater than 1, we have that P of 1, P of 2, all the way up to P of n minus 1 implies P of n. So if P of 1 up to P of n minus 1 are true, then P of n is true. Okay, so before we start with the proof, we're going to state the well-ordering principle, which we're going to need to use in the proof. So the well-ordering principle says that every non-empty subset of z, so of the integers, which is bounded from below, so every set which has a lower bound in z, has a least element. So this is important, and we're going to use this in the proof. So let's proceed with the proof. We're going to let A be the set of positive integers, or natural numbers, such that the statement P of n is false. So we're going to try and show that A is the empty set, and this will prove the theorem. So let's assume that A is non-empty and try and find a contradiction. So if A is non-empty, by the well-ordering principle, A must have a least element, right? Because the set A is actually just a subset of the natural numbers, so it has, for example, 0 as a lower bound, so it's bounded from below, and therefore it has a least element by the well-ordering principle. We also can say some more about the least element because we have some assumptions in our theorem. So by assumption A, this least element has to be strictly greater than 1, because we've already assumed that P of 1 is true. So let's call this least element M. Now, we know, because this is the least element of A, that therefore 1, 2, up to m minus 1 are not in A. But all this means is that P of 1, P of 2, all the way up to P of m minus 1 are all true. Okay, but we can work with this because we also have another assumption in our theorem. We have assumption B, right? And this tells us something about how P of 1 up to P of m minus 1 impact P of m. So we have that P of 1 up to P of m minus 1 being true actually implies that P of m is true. So now we have that P of m is true. And therefore, we have that m is not in A. But this is a contradiction because we have that m should be the least element of A. So the only thing we can conclude is that A is the empty set, which proves that P of n is true for all n in n, which proves the theorem.